Hi, my name's Felix. It's really great to be here in Poland. I'm half Czech and half British, and it's quite interesting to come here to Poland and try to speak Czech to Polish people and see how things go. So those of you who've spoken to me, you might have had some fun. It's mainly just made my head hurt. Actually, this morning, as soon as a taxi driver found out that I was Czech, then he started talking to me in Polish. And just to check if you're awake, I'll tell you what he said, but I'll say it in Czech and see if you understand. So he was, Czech, this is Czech, z České republiky. Jo? Tak. Z Mladá Boleslav, znáš? Město, Mladá Boleslav. Já tam koupil psa, jo? Psa. Jo? Toto je #1 pes v Polsku, jo? Tento pes, #1. Ale moje dcera, rozumíš? Moje dcera mi ho ukradla. Jo? A teďka má 10 psů. Okay. So I hope that made some sense. If you don't speak Polish or Czech, then ask a neighbor or ask me later. Basically, man buys dog. That's the story. So yes, today I'm going to be talking to you about WebGL. So this is something that I like playing around with. This is just an example of one of my projects, kind of like a 3D mountain visualization. Probably when you think of something like WebGL, you see something like this, something sort of 3D, something more like a game rather than a website. And I'm not going to be talking about this today because I think it's quite complicated and it's not very accessible to people. Instead, what I want to focus on is what it is that WebGL actually lets you do. And in my opinion, what WebGL lets you do is access the graphics card from your browser, not just do 3D. And although you can do lots of useful things, with sort of 3D using WebGL, that's not the only thing that you can do. So today I'm going to talk about sort of two things. The first is going to be kind of WebGL basics, and in particular, what's called the graphics pipeline. So how do you get data from JavaScript onto the graphics card and do some kind of computation with it there. And then I'm going to switch into live coding and go through a couple of examples to do with image manipulation, the kind of stuff that you might have seen in Photoshop, so changing color channels or warping and all that kind of stuff. And with this, I hope to kind of explain to you how you can actually write arbitrary code that executes on the GPU rather than just using the CPU where you use JavaScript. Okay, so how do we kind of draw something using WebGL? So there's kind of 6 steps. So the first step is that we create a canvas element and ask it for a WebGL context. So a WebGL context is just like a variable you get back from the canvas. And I like to think of this as like your sort of gateway into the GPU. You could call all your kind of calls onto this object. But this is mostly just to do with kind of setting things up. You don't actually use it that much once your application is running. So once we have this gateway, the next step is to tell the graphics card what we want to draw. We need to upload some geometry into our graphics card so something displays. So in our case, what we're going to do is build a quad, which is just 2 triangles that are put together to form a square. And this is going to be the geometry that we're rendering. So once we know what we're drawing, we have to describe how we're going to draw it. And in my opinion, this is the most interesting bit. So here we're going to be writing 2 programs, one called a Vertex shader and one called a Fragment shader. And these programs get executed, so for the Vertex shader, once on every vertex in your geometry. And the Fragment shader gets executed once on every pixel within your canvas. So once we have these shaders, we have to compile them into a program. And this all happens within the browser. So before this point, these are just strings within JavaScript, and you can manipulate them in any way that you want. And this compilation then happens within the browser and gets uploaded to the graphics card. So at this point, we have something that actually can draw something on our screen. But to add some kind of interactivity and to change things, we need to have a way of passing through data into this program. So we create these kind of links between the JavaScript world and the GPU world using 2 types of variables. So the first is something called a uniform, which is kind of like a global define. This is just something that is available to every fragment and every vertex. And then we also have attributes. So these are things which are kind of per vertex data, that each vertex has something associated with it. So if this sounds difficult, I'm going to sort of break down each bit, so to give you more of an idea of what each of these stages involves. So first of all, getting a WebGL context, this should be pretty self-explanatory. You create a canvas element, you set some properties on it. So here I'm just matching the size of the canvas with the container. you append the canvas to the container, and then at the end, the important bit is you get this context out of the canvas. So once we have this canvas, then we need to draw our geometry. And this is just defined like this. It's just a set of numbers. So it's not very user-friendly. It's just one big array. But what we're doing here is we're defining two triangles. So in the bottom left, you can see -1, -1, and that corresponds to these first two numbers here. And then the next vertex is this 1, -1, and so on. And when we pass these numbers to the graphics card, it knows that we're drawing two triangles and draws them for us. So onto the shaders. So for me, this is the most interesting bit. This is where you actually do all the kind of clever stuff. And I think this is something that's often hidden from you as a developer. You don't really know that this is what's going on, but this is what actually lets you execute arbitrary code on your graphics card. So first of all, a vertex shader. So it's a pretty simple program, and there's sort of two things to notice here at first. So we need to define a main function. So this is what gets executed when this program runs. And the only responsibility of this main function is that we write this variable called GL position. So whatever we output to GL position is the actual final value of our vertex, where it's going to be in our space on our graphics card. So here what we're doing is we're taking the attribute A coordinate, which has been passed in from that array you saw in the last slide, and we're just passing it through to GL position. And we wrap it in like a 4-dimensional vector because that's kind of what the API expects. But for this talk, we're just talking about 2D things, so you don't have to worry about the other two coordinates. So at this point, you might be wondering, what language is this? Is this JavaScript? It's not JavaScript. It's something called GLSL, which is a language which is very sort of similar to C in its syntax. But you don't have to worry about things like memory management or any of that kind of stuff. So actually writing it is reasonably similar to JavaScript. You get sort of functions, if statements, all that kind of stuff. You get a couple of extra things as well. So you might have noticed the vec4, that's just a data type of a vector. So a vector is just a collection of 4 numbers, and this can be anything. Like often it's used to specify a coordinate in some space, or you can use it to specify color channels. So you can have it be RGBA as well. So for now, don't worry about what the varying component is. I'll just come back to that in a second. Before that, I'd like to just talk about a fragment shader. So this is the thing that actually draws every single pixel within your shape. And just like with the vertex shader, then we have a main function, and this has to output something called GL frag color. And the output of this is, rather than a position, is now a color. So the 4 components of this vector are red, green, blue, and alpha. And what I'm doing here is actually passing through this V coordinate. But to do this, I'm using this kind of method called, I'm using this special type of variable called varying. So I'll go back to this slide and kind of explain that. So when we're in a vertex shader, we can sort of look at the value of our attributes because we are on a vertex. But when we're drawing this actual shape, it doesn't make sense to talk about an attribute because we're not on a vertex. We're somewhere in between. So how do we kind of access this value in some way? So for this, we have this mechanism called a varying variable, which is something that you sort of fix to a certain value on each vertex. So that's what I'm doing here. I'm just saying, on this vertex, the V coordinate is the same value as my A coordinate. And then the graphics card automatically smooths between these values for us. And this is how we get this gradient on this slide. Because what I'm doing is I'm taking this smooth value of V coordinate and spreading it across our entire shape. So that's why, as in the bottom corner, we have -1, -1. This is black, because the color channels are all 0 or negative there. And as you move to the right, then you get more red, because it goes from -1 to 1. And as you go up, it goes from -1 to 1 in the green channel. OK, so just to recap that sort of data flow. We've got 3 types of variables. We've got uniform, varying, and attributes. Attributes are the ones which only go into our vertex shader and give us some kind of context on every vertex in our model. Uniforms are just global numbers that we can just access in both these programs. And varyings are these smoothed out values that are only defined exactly on each vertex, and then the graphics card gives us their sort of intermediate values within the fragment shader. Okay, so to recap the whole pipeline, first of all, we need to get a canvas. and ask it for a context. Once we have that, we need to upload some sort of geometry to our graphics card to render. Once we have that geometry, we say how we're going to render it. And that's going to be in the form of both a vertex shader and a fragment shader. And finally, we compile it into a program, pass data into the program, and display this onto a canvas element. OK, so don't worry if that didn't all quite make sense. It's quite a lot to take in one go. What I'm going to be focusing on now is actually writing these vertex and fragment shaders. And a lot of the stuff that I was just saying here is useful as background. And generally, when you write an application, then you set this up once, and then it just works for you. You spend most of your time writing these shaders and living in that world. So even if it seems like, yeah, this is quite a lot of work, think of it just like installing NPM or something. Like the first time it's annoying, but then it's just there. OK, so for my demo, I'm going to be using this app that I've built. And if you want to sort of play around with this, you can, if you just go to this URL up here. What I'm actually doing here is using Firefox, because it has this very nice feature where it has like an inbuilt shader editor, which you can enable here in the developer tools. And what this lets us do is sort of take the shaders that are being used in our application and change them in real time. So you don't have to use some kind of IDE or anything like that. You just have it all working within Firefox. So what I have here at the moment is pretty much what I was showing you on the slides. I've got these two programs, a vertex shader and a fragment shader. And here I'm passing in some kind of coordinates. This coordinate then just basically gets passed on to GL position. And it gets also set to this V coordinate, which gets passed down into here, into the fragment shader. And then this is used to define some color, which is drawn here. So now I'm just going to go through a bunch of image manipulation tricks to kind of give you an example of how you can write code here and all the effects that you can get working here with sort of hardware acceleration. So the first bit I want to talk about is scaling and transforming. So this is the kind of stuff that makes a lot of sense within the Vertex shader. So the easiest thing to do is take our vertices and scale them down a bit. So to do this, I need to define some kind of variable here. I'm just going to call it C, which this doesn't like. Yeah, because it's not a float. And now what I can do is I can just multiply this by some constant, and this has the effect of shrinking our square. Because what was a vertex before that was 1, 1 becomes now 0.9, 0.9. If I want to translate these vertices, I can do more or less the same thing. It's pretty self-explanatory. So something like this, and this shifts the whole square along. Now, recall that I was talking about passing data to and from the GPU using uniforms. So what I have set up here is this kind of control panel, which is just controlling some JavaScript variables. And every time we render, then we upload these to the graphics card. So what I can do here is I can define a uniform like this. So this gets the value of this A parameter here. And then rather than using just a static value here, I can use this. And then as I change the value of this slider, then this goes up and down. And this is quite nice because to make this change, I don't have to change the program in JavaScript. I don't have to recompile it or anything like that. I just have this direct link into this GPU world. And it's sort of very, very performant doing it this way rather than recompiling the program. So the final thing you might want to do is rotation. And I'm not going to cover exactly how you do this because you need to use a matrix, which might be something that's not familiar to all of you. But if you look at my code, then you'll see it. It's, again, just one line of code. It's not that hard. OK, so to move on to something more interesting than just gradients and solid colors, then we have to introduce textures. So the graphics card also has a bunch of texture slots on it into which you can upload arbitrary data. So often this might be images, but it could really just be anything you want to do kind of general computation on. So what I've set up here is I have just like a Dropbox with various images in it. I'm just going to go and get rid of this for now. No, I shouldn't have done that. Just to make it full screen. And now onto the fragment shader. Here, rather than playing around with this V coordinate, I'm going to load in this texture. So again, this is just going to be a uniform. This time, rather than being a float or a vector, I'm going to use this thing called a sampler 2D I can just give it any name. And then to set my color, I'm going to do a lookup into this texture. So for this, we use a function called texture2D. And what this takes as parameters is the texture you're looking into and some position within the texture. So if I just pass in 0, 0, then this will be looking up the topmost pixel of this texture. So in this case, it's something that's blue. If I change the texture, it'll be something that's green. So this isn't great. What we actually want to be doing is on every fragment within our canvas is to look up a different pixel within our texture. And you can probably guess how I'm going to do this. So rather than just putting in a static constant here, I'm going to use this v coordinate. And voila, we get our texture in. So you might notice this is a bit broken. It's all kind of stretched out and upside down. And that's just because v coordinate is in the range -1, 1, and this texture expects 0 to 1. So this is just something I'll fix in a later slide. I wouldn't worry about it right now. OK, so now I'm going to move on to talking about some sort of simple color effects. And for this, I'm just going to quickly switch out the program that I was using, so I don't have to do quite as much typing. But it will more or less be doing the same thing. OK, so now you'll notice that we are getting our picture drawn in the right way. And that's just because I did that transformation that I was talking about. So rather than thinking of the coordinates in this space of -1 to 1, I've switched it to be in this texture coordinates of 0 to 1. And for the rest of the talk, we're going to be thinking more in terms of this parameter here, something called UV, rather than in this parameter coordinate. So UV is just something which in the bottom left of our texture is 0, 0, and in the top right is 1, 1. So it's just a more natural coordinate system to work with. OK, so on to the color effects. So this file has got a lot more sort of functions here, but really I'm not using these. These are just here for reference if you want to play around with it later yourself. The really important bit is just these 2 lines at the bottom, which is just the same as what we were doing before. So we're just picking a color from a texture, looking it up in this texture slot, and using UV to index into the right place. So at this point, if we want to do some kind of manipulation on the color, then we can play around with it before we output it to this variable GL frag color. So if we just want to change 2 channels, it's just as simple as something like this. So this just swaps the position of these 2 vectors. And there's lots of kind of nice little shorthands like this in GLSL. If, for example, we'd want to turn this image into grayscale, then what that actually means is that we want to take the value of this color vector and make all the components the same length. So again, that's kind of simple enough. All we need to do is get the length of the vector, like this. And this isn't going to work right now because it's telling us that length is a float and color is a 3-component vector. So all we have to do is just convert it back into a vector like this. And we get kind of a grayscale image. So now that we know how to do that, we can start doing something a little bit more interesting. So for example, we can start isolating one color within our image. So I'm just going to switch to a slightly different picture of one of my favorite cats. And what I'm going to do here is I'm going to try and figure out which pixels are green, so sort of pick out the grass region and do something to them and not apply that same transformation to the actual cat. So one easy way to do that is just to have like an if statement which has a look at the pixel and says, OK, if my color red is actually quite low in this region, then it's probably the grass. So do something there. So I'll only apply this transformation to that kind of region. And then as I change this threshold, then I can sort of select just the cat or everything. So you can apply this kind of conditionally. OK, so I'd like to move on and talk a bit more about some other effects. So now I'm going to talk about blending multiple images together. So the way I've got this set up is I've got these functions which just help me out in terms of loading things in. So the value of gradient is just my gradient image, and the value of image is just my image. So if I want to just draw the gradient, I can just assign the color to that before outputting, and I get the image. Now, if I want to mix these 2 things together, what I can do is use this mix function, which takes three parameters. So the first one is some value. The second one is another value, so in this case, the image. And then the third one is the kind of the mixing factor between the two. And again, I can assign this to one of these parameters, so we can play around with it and sort of smoothly blend between one and the other. But here, we're not restricted to just blending these things based on some static value. We can look into some kind of parameter that varies across our image and blend using that. So what I can do is use this UV parameter, which is, recall, what we're using to look into our texture. So it varies across our image from 0, 0 in the bottom left to 1, 1 at the top. If I take the X parameter, then this basically means I'm going to smoothly vary from the left side of the image to the right side of the image between this gradient and the actual original image. But this is kind of like a wide spread. So we can make this a little bit better by using what's called a step function. So a step function is something which kind of compresses this range. It basically returns 0 if this parameter here, UVX, is lower than UA, and 1 otherwise. So using this, we can sort of scan between these two guys. And we can take this even one step further and use a function called smooth step, which takes two values and sort of merge them in a kind of more sort of pleasing way. So everything that's below A becomes a gradient, and everything that's above B becomes the goat, and everything in between is just blended like this. So often it's useful, rather than thinking in terms of UV, to think of this image in what's called polar coordinates. So this is a system of coordinates where, rather than thinking in X and Y, we think of how far am I from the center of the image, and what is my angle relative to that. So that's what I'm doing here. I'm doing this kind of transformation between my UV coordinate system into polar and then back. So rather than triggering here based on UV of X, if I trigger based on my polar coordinates and adjust this to something nice, then I can get an image that blends in this way. And if rather than using the gradient and the image in this way, I use the color black, then we get this kind of nice sort of vignette spotlight effect on our image. And again, just can change sort of exactly how strong this is using these parameters. Okay, so I hope you're still with me, because it's going to get more complicated. So now I'm going to talk about some warping effects. So the first one is just stretching the image. So I'm just going to be doing the same trick again and again and again, just a bit more complicated each time. So the general idea is that before we look up our texture, we do something to our UV coordinate. So the simplest thing that we can do, well, it's not the simplest, but one of the things we can do is just square this coordinate. And the effect of this is the numbers at the left kind of get stretched out, because 0.1 becomes 0.001, and the ones on the right, which are close to 1, don't really change very much at all. So it's not very interesting doing this in UV space. Again, it's more interesting to move into polar space, where if we change the way the kind of the distribution of the radius, we can get this kind of nice sort of fisheye effect. And if we want to control it even more, then we can just change, actually I'll just use UB. So we can just raise it to an arbitrary power, and then as we sort of move out, we kind of can do this kind of thing. So you can do mean things to animals this way. So the next thing we can do, if we're not sort of having enough fun with pinching, is do something that's called a twirl. So here what I'm doing is I'm modifying the radius. And if instead of modifying the radius, I modify the angle, then it's going to sort of give us a rotation. So if I just put it to a fixed angle like this, that has the effect of rotating my image, like so. But if I want to do something that's a bit more fun than this, in this case a twirl, then I can make it so that the further you are away from the center of the image, the more we apply this effect. So if I just multiply this by the radius, then in the center of the image, we're not going to be doing very much of a rotation, because R is very small. And then the further away we get from it, the more we can do this. So yeah, again, quite fun. You can also do it on a cat, I mean. Cool. So now it gets more interesting. Rather than just twirling stuff around, what if we define some kind of deformation across the whole image that was periodic? So to do this, we want to use some kind of sine function. So if I go and just type this out, say like that. And just to give you an idea what this looks like across our image, I'm just going to output it directly to color. What have I done? I feel like I've done something wrong here, and I can't think of what it is. Oh, yeah. Yeah, so we want it to be something that changes over the course of our entire image, so I have to hook it into this UV of X. And for some reason, this is giving me a bug. I'm not sure why. Can anyone see the bug? Get chocolate if you spot it. Sorry? Yeah. Oh, yeah. I have to do this first, obviously. OK, sorry. So what I've got here is some kind of value that varies across our image. And the frequency with which it varies is just controlled by this parameter, and the intensity is by this one. So if I then take this field and I use it to deform our lookup into our texture, then we're going to get like a wavy effect in our image. So all this is then just adding this constant A to our UV parameter. So I'm just going to modify UVX by A, like so. And now just to get rid of this color, I'm going to get an image that looks something like this. So we kind of get this sort of wavy effect. And it's a little bit too strong at the moment, so I'll just make it a bit weaker. So something like this. So this is kind of fun. And to make it even more fun, what we can do is rather than just having uniforms which are static with time, we can pass in something that JavaScript is changing for us automatically. So I have a uniform that's also just called time. So if I pass this in, then as time goes on, we're going to get this wave effect moving in an animated way. I can slightly speed it up, like so. So you kind of get this effect of waves going across the image. And again, we can do the same trick, but rather than doing it in UV space, we can do it in polar space. So I'm going to take this guy, and rather than doing the transformation on UV, I'm just going to do it in polar. And rather than applying the change to UV, I'm just going to apply it to polar, like this. So we end up with this kind of, if I try and make it look more like water, yeah, this kind of sort of effect like so. OK, so on to the last section. Here I'm going to be talking about pixel effects. So again, it's the same kind of trick. We want to somehow modify our UV parameter before we do our lookup. But rather than modifying it in a way with some kind of field or deformation, we want to snap it to a value. So to get a pixelated effect on an image, that basically means that sort of large blocks have to be the same color. And to get that effect, we kind of want to use a floor function, like this. So what this function does is it takes any number, if it's like a float, and just rounds it down to the nearest integer. So if we apply this to UV directly, then all our numbers just get collapsed into 0. That's not what we want. What we actually want to do is multiply it by some constant here, and then divide out by that constant. And this has the effect of sort of quantizing our numbers into sort of ranges. And again, rather than using something hard-coded, I could make it something variable, and using this kind of play around and change how pixelated my image gets. So with this in hand, I can do the same trick as what I was doing at the moment, what I was doing at the beginning with the cat, and apply this to just one region of the image. So I could say, OK, if it's green, don't pixelate it. If it is, then pixelate it. But because my screen is flashing here, I'm not going to show you that. and move on to the conclusion. Oh, actually, notice there's one thing which is blurring. This is quite a lot of typing, so I won't show you this directly. But basically, it comes down to rather than doing just one lookup into your texture, then you do lots of lookups in a neighborhood and just merge the values. So if you just take a look at the code up here, there's a function called draw blur, and it should be it's quite verbose, but it should be quite self-explanatory. Okay, so sorry if that was a bit quick. It took a little bit longer than I was expecting. But by way of conclusion, I hope that if you take just one thing away from this talk, it's that WebGL isn't just something that you can use for 3D graphics. It's more just like a gateway into accessing the second processor pretty much everyone now has available on their computer. And this is definitely a trend that's been happening outside of web development. And I hope that in web development in coming years, then more and more tools are built which let us access both the CPU and the GPU. And I hope this talk has kind of opened your eyes a bit to what you can do there. So with that, I'll say thanks, and any questions?
Hi, great presentation. Well, I have a question regarding the textures. So the texture has like a physical dimension, like 256 pixels per 256 pixels. And you said that the coordinates used are in the range of between 0 and 1. So how actually the pixel colors are calculated when we hit into something like in the middle of the 2 pixels? Are they averaged or something like that?
Yeah, it's a good question. So it's true that no matter how big your texture is, when you're talking about it on the graphics card, it goes from 0 to 1 when you're addressing it. That just kind of makes it easier. The way you actually interpolate between pixels in the original data depends on how you configure the texture to work. So the simplest way is that you just kind of pretend each pixel is a square, and if you're inside that square, you read that, and you don't do any kind of smoothing. But that looks terrible in a lot of cases. So what you do is you have different types of filtering, and the graphics card just kind of does all of this underneath the covers for you. So it you kind of have 2 problems. One problem is the one that you described, so you are zoomed in so much that you'd see the detail. And then the other problem is your texture's been scaled down to something, and what do you see? So it's quite hard to explain this just on stage, so if you want to just chat afterwards about it, we can. But basically what it comes down to is you have different filtering methods that you can specify on your textures, and the graphics card just handles all this stuff for you. And it's kind of important to realize that it's doing this, because if you try to do a lot of these effects in Canvas, just like writing it out, then they might sort of look okay, but you're going to end up with lots and lots of artifacts. And without all this texture filtering, you won't get it looking nice and smooth, especially with like the pinching and the twirling and all that.
Hi. So is there a way to handle like really big images, like taken from a camera or something like that?
So the fun thing about WebGL is that you don't only have to worry about the browser, you also have to worry about the graphics card. So different people are going to have different graphics cards, and these give you kind of different levels of performance. So in general, you're pretty safe if your texture is 2000 by 2000. That basically hits everyone. I think you get 90% of people if you do 4000 by 4000. And for example, this computer, I can do 16,000 by 16,000, so like a huge texture. So I think already 4000 by 4000 gives you quite a lot that you can sort of work with. But I mean, if the computer just isn't powerful enough, it's just not going to work. But there's nothing in the spec itself that stops you.
Have you found similar image manipulation web apps online that use Canvas?
Yeah, so if you, there's one that's called a GLSL.io, which lets you kind of program transitions between 2 images. And that's kind of doing this sort of stuff, but it's a lot nicer than what I have. And I think if you kind of Google the relevant sort of search terms, you will find some other people who've done kind of similar things. So there are a couple of things there. I also think there's something called Pixie.js, which is kind of like a framework around building sort of 2D things in WebGL. What I've tried to do here is build something without a framework, just to show that you don't need something like Free.js to kind of get started. Okay, well, thanks.